All right, so we're gonna start this webinar from RADNEXT facility webinar series. My name is Ygor Aguiar from the Project Management Office of RADNEXT project, and today we will host this webinar together with my colleagues. So we just share my slides quickly. You cannot see maybe the correct slides. Voila. So for those who are not familiar with RADNEXT, RADNEXT is a European project with the main goal of enhancing the accessibility to accelerate infrastructure for the qualification of electronics components. And up to now, we have provided already about 5,000 hours of being time. So we want to provide enhance this accessibility through scientific research, but also providing transnational access to irradiation facilities in Europe and in Canada. So we still have two calls for proposals left in the project. So the next one will be in May. Starting from the 1st of May, we will be receiving proposals, and we're gonna have different type of beams available. So from atmospheric neutrons, thermals, to different types, energy of protons, heavy ions, and so on. For all the requirements and the information needed to submit your proposal, you can check our website. And also, if you have questions, don't hesitate to send them to our contact here. So if you still don't follow our page on LinkedIn, this is the best way how to get informed about all opportunities within the RADNEXT project, the different being times, the different events we're organizing, the webinar and so on. So please be sure to follow us if you don't want to miss out on the different opportunities. Also, we have a repository for the transnational access irradiation campaign. So the users provide a short summary of the irradiation plan and the irradiation carried out through the transnational access in RADNEXT. So if you're interested of knowing what has been done and what you could do, I think this is a good source of information for your project as well. So for today's webinar, I have the pleasure to have here my colleagues at CERN that we talk about HORTS project, where we can provide high energy heavy ions beams to qualify electronic components. For the next webinar, we'll be also talking about heavy ions, but from a facility in US. And we also had before other facilities talking about the heavy ions, for example, as in the NASA Space Radiation Laboratory, and we have other coming up in June. So please, if you follow the channels, you will be informed about the next ones. And if you couldn't attend to the previous webinars, you can always check our YouTube channel where we upload the next webinars as well. So as I mentioned, today's topic is the HORTS project at CERN, and I have the pleasure to introduce here my two colleagues, Natalia and Andrea, that are heavily working on the development of this beam line at CERN. And then we will talk more about the challenges and how we can apply for being at HORTS. So this is my cue. Natalia and Andrea, the floor is yours. I will stop sharing so you can share your slides.
Thanks a lot, Igor, and good afternoon to everyone. So Natalia will share the slides. I will also switch off my camera. Apologies for this, but I'm in Spain for the moment, and the network is still recovering from the blackout from yesterday. So if I cut out at any point, and if you missed something, then please don't hesitate to ask in the question session after the talk. So yeah, thanks again, Igor, for the introduction. So today, Natalia and I will talk about HORTS at CERN. since we're never really sure about the audience and the background, I will give a short motivation or introduction, let's say, to the topic before Natalia will dig into the specificities of the facility. So if we go to the first motivation slide, if it's coming up, yes, great, thanks. Okay, yeah, then we can directly jump to the next one already. So yeah, basically, when we are here, when you're on Earth, we are, let's say, protected by the atmosphere and the magnetic field of the Earth. But if we want to do anything fun in space, then any object that is supposed to operate there, so in the space environment, is continuously subject to energetic particle radiation, and we can discern two main radiation sources. We have solar particle events, which are, of course, creating the beautiful northern lights we also saw pictures of, but also galactic cosmic rays, which are a bit higher in energy, and they are composed of a lot of different particles. So we have to take into account the potential radiation effects that these radiation sources can cause when, for example, we're venturing to the moon or Mars, as are the plans of the major space agencies around the world right now. These particles, this radiation, can transfer energy to biological tissue. So of course it's a health hazard, but also to spacecraft material and of course electronics, which is going to be the main topic for today, in both a stochastic or probabilistic way and a cumulative way. So a deterministic way that if you venture into space for a long time, that you will add up the effects, let's say, from being there for a long time. So next slide, please. So if we talk about these two main radiation sources, as I mentioned, the solar particle events, actually the energies that are associated with this type of radiation is far lower than GCR. So that's why we're only going to be talking about the GCRs here. They're for the SPEs, it's order of tens of MeV, and that makes them far easier to shield compared to the GCRs, which peak at energies between 300 and 1 GeV per nucleon, and this makes them a very highly penetrating form of radiation. In the GCR particle spectrum, we find all particles. Hydrogen is the most predominant, let's say. And for 1,000 hydrogen ions, we get one lead ion. You can see it in the tiny peak there. Very important for testing for radiobiological effects for astronaut health hazards, let's say. And just mentioning the lead ions, because that's what we're using at CERN for radiation effects testing. You get 1 billion hydrogen ions, then you get one lead ion that is impingent on your spacecraft. Next slide. Thank you. Digging a bit deeper into the physical basis. So what happens when these type of particles are interacting with matter? So at these energies, they slow down in matter through energy loss, the EDX or the LET. These are the way that we are addressing this phenomenon, let's say, and usually expressed either as a kilo electron volt per micron, or MeV centimeter square per milligram when you are normalizing by the density of the material, as it's usually done in the electronics testing context, let's say. But we don't only have energy loss, we can also have fragmentation at these energies, because we're far above the Coulomb barrier at these energies, and so we encounter inelastic nuclear interactions with any matter, which can generate a lot of secondaries with also potentially high linear energy transfer. So again, they create particle tracks, and a single particle track can deposit sufficient amount of energy in a sensitive volume of, in particular, an electronic device, to trigger a stochastic or probabilistic effect called a single event effect. Specifically for electronics, so we call it a stochastic effect because the probability is for triggering an SE is proportional to the dose. So this equals the product of the particle fluence and the LET. These are two main dosimetric quantities that we'll talk about a lot during this talk. But of course, other factors, non-fluence and non-LET, can play an important role as well. Usually, we talk only about LET as the metric for testing, but particle species can have an effect as well. We saw that there are a lot of different particles in the GCR spectrum. Usually, in the radiobiological context, we care about this much more, and in the electronic testing, we only care about the LET. Other than that, we have the particle strike location and angle, of course, the impingent material. If you're considering a silicon device or a silicon carbide device or gallium nitride, this makes a difference. The exact transistor structure, the bias of the device temperature. Of course, I mentioned deterministic effects already before. When you're in space for a very long time, you have to worry about the total ionizing dose and displacement damage to the lattice of the device itself, which can then, in combination with single particle tracks, can generate synergistic effects. And when you're looking at a larger scale, there's the response of the circuit in which the device is embedded and the operating speed. So we can, let's say, trigger a myriad of different effect types, depending on the device itself or the outcome. We label them single event upset, latch up, single event burnout, gate rupture, or a functional interrupt. And the common ground here is that they can all adversely affect the reliability of a system to be flown in space. So how should we address these potential adverse effects? We have the way of addressing this under the term radiation hardness assurance, which is an iterative process and consists of all the activities that are needed to ensure that potentially radiation sensitive units of a system, including the system itself, of course, will meet their design specifications for the mission under study, or that want to be carrying out. So of course, depending on the mission profile, there are different radiation environments to be encountered. The orbit can play a role in this. If you're staying in low Earth orbit, or if you're venturing to the Moon or Mars, this of course makes a difference. There are simulation tools that can help to assess if single event effects or the rate of single event effects is going to be an issue or not for a certain device. And then, of course, within this hardness assurance process, there is the testing, of course, which is playing a big role and is what we're going to be addressing today. So in the next slide, just recapping, let's say, a bit the basics. If we want to do the radiation hardness assurance of a certain electronic part, what is happening is we try to calculate the single event effect cross-section, which again can be obtained as a function of the LET by simply counting the number of SEs during a test for a given particle fluence. And here we're always talking about in dedicated accelerator facilities where these tests are carried out on Earth before a space flight, is to get LETs that are representative of the GCR spectrum that you find in space. And for this, we use heavy ion beams, for example, testing at the infamous 37 MeV centimeter square per milligram, which is supposed to be, let's say, kind of a maximum limit of what you encounter in space, even though there's a bit of debate on this. But the bottom line is that during the testing, SEs are triggered in an accelerated fashion compared to the space environment. We determine the radiation tolerance of a device by obtaining the threshold LET, so really the LET where the device is starting to make a response, and the saturation cross-section. And based on this, once you calculated this, we can actually go back to the GCR spectrum, fold the cross-section with the spectrum, and obtain a single event effect rate that you might encounter when you're embarking on a space flight. So talking about these heavy ion beams that we have in the accelerator facilities here on Earth. The thing is that depending on the energy, the penetration capabilities of these ions is very different. So talking about the facilities that we have in Europe, for example, UCL and RADEF, there are two facilities that have heavy ion beams at fairly low energy. You can see for this, let's say, kind of a representative modern device, which is an almost 200 layer flash memory. The particles, they don't penetrate very far. You go to medium energy facilities like Ganil or UCMG in the Netherlands. This is a bit better. But the testing with higher energies is actually becoming the only solution to make sure that you are able to penetrate all the layers of the device and making sure that your device is assessed for the response that you can expect in the space radiation environment. So this very high energy testing regime, which is also where HARTS at CERN is going to be operating in, is between 50 MeV per nucleon and 5 GeV per nucleon, and is what is the most interesting, let's say, to assess state-of-the-art components. So these very high energy heavy ion beams, they have important differences compared to the lower energy and the standard energy beams. So if we recap the calculation of the single event cross section, remember this factors in the LET of the beam and the fluence as well. It is not, let's say, so unambiguously defined as in lower energy or medium energy facilities, because what is going to happen is that because of the nature of the energy of these beams, it's exactly the same thing as GCR particles in space. You get fragmentation with basically any material that is in the beam path. And the benefit of using these beams is actually testing in air. This usually means having vacuum windows, but in addition also beam instrumentation to do the dosimetry. You will have interactions with these materials inevitably, and you end up, instead of with a single LET at the test location, with a spectrum of particles that you need to take into account and that potentially affect your test. Not only that, not only on the level of the LET, but of course also in terms of fluence, you get a flux attenuation of primary particles because they basically interacted away. So that's on the level of the beams itself. If we then go look into the devices that we want to test, which are modern microelectronics, it's perfectly possible that within the device there is an unknown material budget, which actually means that this propagates into an uncertainty on the LET within the device. The sensitive volume is located at a specific spot, at a specific depth, under a certain amount of material, and it becomes increasingly difficult, certainly when you're operating close to the Bragg peak. So when you're wanting to test at very high LETs, there you get a high uncertainty. You can see it on the figure on the top right. Basically, when you are crossing 300 microns of silicon and you're doing this at a low LET, you are still at the leftmost side of the Bragg peak, let's say. There is not much variability in terms of LET. However, if you're already going to a depth of 1.5 centimeters or even beyond that, very close to a Bragg peak, so close where the particle is going to stop, there you have a variation of almost 20 LET points, so quite a lot. Because of the straggling of the energies of the particles, which is also happening in a, let's say, rather probabilistic way, there's an uncertainty on the particle range within the device, and you're even not even sure if the sensitive volumes can be reached. So to summarize here, you're not taking into account the LET and the fluence as fixed values, let's say, but you're looking at an energy deposition distribution and a range distribution and primary fluence attenuation when calculating the single event effect cross section. So that's specific for using very high energy heavy ion beams for testing of modern components. Just to mention here that, of course, is something that we all see happening, is that there is an exponential growth of satellites, certainly with the emergence of the mega constellations that are being built right now in low Earth orbit. There is just a vast increase in the amount of objects that are launched into space, and the performance of these systems is increasing, which means that to keep the cost at a reasonably high level, reasonably low level, sorry, let's say, means that we are looking at COTS components, so commercial off-the-shelf components, because they're also more available than dedicated rad-hard devices are needed to drive these technologies forward. Now, the lower cost of COTS components does not mean that the total cost could be lower, because actually the estimated full cost of characterization of a COTS device is on the order of 10 to 100 kilo US dollars, depending on the complexity. So most costs are linked to the labor during the test development phase, which means that here there is really an increased importance of developing more performant and more efficient test solutions for these parts. In particular, in the context of using very high energy heavy ion beams, I mentioned it already. The penetration capability is very high because of the high energies. You have a very large range in silicon material. You can test in air, which removes the need for deleading or decapsulating the component, allowing to, if you manage to stretch out your beam, let's say to a large beam size, to be able to radiate large test batches and perform board level testing. So going to indeed the demand here, as mentioned, it is becoming increasingly difficult to test a COTS component at conventional heavy ion accelerators, simply because the penetration capability is not that good when compared to very high energy beams. However, these very high energy heavy ion beams are simply very, very scarce. There are not too many accelerator facilities around the world that are able to provide these type of beams specific for radiation effects testing. So the current heavy ion beam time at all energies worldwide caps up at about 10 kilo hours. In Europe, it's around 3 or 4 kilo hours of beam time that can be offered. NSRL, the topic of one of the previous RADNEXT webinars, is worldwide the only high energy heavy ion dedicated test facility for space users. There are the facilities Riken and HIMAC in Japan, with no, let's say, routine access for electronics testing, but rather a focus on radiobiology. And CERN and GSI in Europe, no routine access yet, and with a focus on nuclear and high energy physics. And in the scope of the exponential growth of satellites or objects that are getting launched into space, and the let's say monotonic increase only of beam time being made available in test facilities, there we're looking at a supply gap of another 10 kilo hours in the coming decade. So this is where HARTS jumps in, since we mean to address this gap. HARTS has an ESA-sponsored predecessor. It's called the Chimera activity, where we're able to rely a lot on the European Space Agency's expertise, and this, let's say, followed up with the EU Space Research and Innovation Program, part of Horizon Europe. Expanding Europe's accessibility to very high energy heavy ion beams for space radiation effects testing. Specifically, we're going to talk about HARTS at CERN in this case, and we are trying as much as possible to leverage CERN's infrastructure, its scientific program, which of course is shared with the other users of the accelerators, in the use of lead ion beams, but also the expertise that is present at CERN to provide commercial beam time and access for external users. So just a quick word about the HARTS project. If you want to have more information, of course, you're very welcome to visit the website. It's a project that kicked off in 2023 and will finish in 2026. The consortium is composed of the two high energy heavy ion facilities in Europe, CERN and GSI, and trying to achieve complementarity between the two facilities, and still the amount of beam time that we are able to offer the both facilities, let's say, is still not really big. And we're trying to achieve the complementarity, being able to do the same test or a similar test in both facilities, and achieving the same results. So we have the two facilities complemented with space industry and academia partners, Airbus, Thales Alenia Space, the University of Padova and COSI-Lab. And just a very, very quick word that within the project very early, we talked a lot about establishing, let's say, beam requirements, because the testing with very high energy heavy ion beams is a fairly new domain. So a document was made which, let's say, acts as a standard or as a protocol which exists already for single event effects testing in the form of ESCC or ECSC. Guidelines for testing, not specifically for very high energy heavy ion effects testing, with the following requirements on the LET, providing 3 to 5 steps in a very large range, but having a not too big uncertainty, plus or minus 10% in LET. Same goes for the flux and fluence, and being able to tune the beam flux within a large range, as is standardly used for single event effects testing, and achieving large beam areas. And in addition to that, being able to provide the service that is present at other heavy ion facilities around the globe, to be given a good context for testing. And with that, I hand over to Natalia, who will go into the details of the facility itself.
Hello, everyone. Okay, so now let's go to the details about the hearts at CERN, starting with the facility description. So here is the schematic of the CERN accelerator complex. You see that it is composed of many different accelerators that are interconnected in a complex chain. And the smaller accelerators are used as injectors for the larger ones in the acceleration chain to ultimately deliver particles to the Large Hadron Collider for high energy physics experiments. In addition to this, we also have a plethora of secondary beam lines that are extracting beams from the injectors already for many additional experiments. So in this CERN accelerator complex, we are operating with protons and lead ions, and that's where the HART project can leverage the CERN infrastructure for heavy ion testing of electronics. Indeed, there is a dedicated ion physics run in the SPS and the LHC during 2 months of the year, so always at the end of the year. And this gives a potential of 2 to 3 weeks of heavy ions for the HART project. So where in this complex existing infrastructure we can see the HART project. So it is happening in this color part of the complex here on the bottom. So the required very high energy that is suitable for electronics testing can be extracted from the proton synchrotron accelerator here, that is the CERN workhorse for many different experiments. And this has implications on the beam that we can obtain. So first of all, the proton synchrotron, as the name indicates, is a synchrotron, and therefore the beam is pulsed and is delivered in so-called spills. So unlike the more standard facilities where the beam is delivered in a continuous way from a cyclotron. In addition, there is a duty cycle, so we receive a spill in average every 10 seconds, but this is also subject to the so-called supercycle composition, which simply means that it depends on the current use of the complex, because we have to cope with whatever experiments are already taking place without disturbing them. So when the complex is more busy, we'll receive a little bit less. And when there is more experiments running at the same time, we receive a little bit lower rate of spills. And the fluence of 10 to the 7 ions per centimeter squared, that is typically the goal for an electronics test, can be achieved in minutes or tens of minutes with the PS beam. So let's focus now a bit on this acceleration chain here that we can use. So the heavy ion path starts in the ion source, where the lead ions are evaporated from an oven. Then they are injected here to the LINAC 3 accelerator, where they can be accelerated to 4.2 MeV per nucleon. Then the beam is injected into the low energy ion ring, or LEIR. You also have a picture here, where the beam is further accelerated to 70 MeV per nucleon. And then they continue to the proton synchrotron, where they can reach up to more than 5 GeV per nucleon. So we find here the energy of heavy ions that is of interest, as it was explained by Andreas, between, let's say, 52 MeV to 5 GeV, and 5 GeV is even a little too high for electronics testing. To extract the beam and use it somewhere, we use the so-called slow extraction technique of spills that can reach a duration of up to 1 second. And the slow extracted beam is then transported to the East Area test hall, where it can be used in a test facility. Here is the 3D view of the East Area test hall, where the beam extracted from the proton synchrotron, of which you see a portion here, can be then sent on different existing beam lines. So we have 4 of them, named T8, T9, T10, and T11. So for our application, we use the T8 beamline, which is this one here, because on this beamline, we already have 2 existing facilities that we can put to contribution. So the more upstream facility called IRAD is typically used for direct irradiation with the 24 GeV protons of small and often passive samples, while the other facility, more downstream, just before the beam is dumped, is called CHARM, was built for electronics testing in a radiation mixed field that is produced by sending the protons on a target and then using also a combination of shieldings. So this is where we can find the ions of interest for the use for electronics testing and qualification. And here is a little bit of a timeline of the development of this capability at CERN. So we started already in 2017 and 2018 with some first demonstration of the possibility to extract the heavy ions from the PS to the East area. This was mainly within the Radiation to Electronics project in collaboration with ESA. And we also did first irradiations with a fixed energy and fixed intensity. In this case, it was the maximum energy, which is a little too high for the target use. Then this activity continued under the umbrella of the Chimera project, as it was mentioned by Andreas. This project was co-funded by ESA and took place in 2021 and 2022. In 2021, we had 1 day of beam time where we made attempts to lower the energy and also control the intensity. And in 2022, we had 5 days, during which the ESA colleagues also came on site and performed their own tests and calibrations. And we demonstrated the energy and intensity control over large ranges. So this was the goal of the Chimera project. And then the legacy of this is now the HARTS project, which started in 2023, where we had 2.5 weeks of beam, and we focused on beam development and calibrations, as well as enhancing the user readiness of the existing facilities for the new application. And then last year, again, we had another 2.5 weeks, and we performed the first pilot run with external users that I will talk a bit more about later. And another HARTS user run is upcoming this year. So in which of the 2 facilities we perform these various irradiations? Historically, from the beginning of the activity till 2023 included, we were working at CHARM, which is the downstream facility, and our test location was here at the very end of the T8 beamline, just before the dump. The choice of the CHARM facility was natural because this facility was built for electronics testing, so the infrastructure, connectivity, etc., is well suited for the use. However, the bottom line was that both of these facilities are operating fully in air, and therefore the beam has to cross about 30 meters of air, let's say between here and the old test location. And that's why from last year, we moved the HARTS at CERN activity upstream from CHARM to the IRAD facility here, and we started taking beam at the very upstream of the IRAD facility at the exit of the vacuum beam pipe, which improved the beam quality and also allowed to extract a lower energy from the machine and transfer it to the test location. And this is how the HARTS at CERN in IRAD looked like last year. So we have the beam coming here from the right. You see a portion of the vacuum pipe. Just after, we have a set of PMMA degraders to adjust the beam energy locally. We also have a couple of tungsten masks to shape the beam, and the beam profile monitor to visualize the beam just before it reaches the component to test. And here you see our new test station, which is used with the so-called ESA frames, where you can mount the devices for the irradiation. And the patch panel to connect the devices to the outside is here outside of the picture, just here on the wall. So the first piece of equipment that is hit by the beam after the beam pipe is the Hertz degrader system. You see some more pictures of it here. It was designed and produced at CERN, but it was largely inspired by the well-established facilities, namely NSRL and GSI. It is fully remotely controlled, and you can see a nice 3D picture of the control system that we have. It features 7 PMMA degraders, currently going from 0.5 millimeter to 20 millimeters that we use to adjust the LET locally. Then we have 3 tungsten masks that you see a bit better here. They are basically blocks of tungsten with a square cutout in the center with 3 different openings to shape the beam into a square beam profile. So we have 3 different beam sizes that are squared with a side of 75, 50, or 25 millimeters. And then finally, this golden object here is the beam profile monitor, which is a multi-wire proportional chamber. Then the test station was also designed and produced at CERN last year. It is also remotely controlled. We also have a very nice control system, of which you see the 3D here. It allows for X and Y translations and 1D rotation around this attachment axis here. So the devices to be irradiated are mounted on the so-called ESA frame, which is becoming some kind of a standard in the community. But you have a picture of a couple of those frames here. They are 24 by 24 centimeters with a lot of holes all around where you can fix the devices. And so with this test station, the beam center can cover the whole frame, but since the beam is large, you can also extend a little bit outside as well. We have the possibility to save predefined positions, so users can deploy several devices on the frame since it is quite large and then test them sequentially without accessing the facility. And the coordinates are logged along with the timestamps, and these logs can be provided after the test. There is also a second static frame behind that you see on the 3D, which can be used for either deploying an extra beam diagnostics device or to perform parasitic or parallel irradiations. So the system worked reliably last year, and we hope it will continue this year. And here are some more equipment from the IRAD facility. So we deploy the ad hoc copper beam dump that you see on the picture here. It's just basically a cylinder of copper that is enough to stop our ions and prevent them from continuing in the downstream part of IRAD and CHARM, because there are some samples and the cryostat that are cooling down during our test. And here you also see the picture of the IRAD patch panel that allows to connect devices to the control room through 16 meters cables. A word on the upgrades foreseen for the 2025 ION run. So we are also working on the deployment of a new laser alignment system. Up to here, we used the laser system inherited from the IRAD facility, which consisted in putting in place a laser manually in each axis, and it was also shining on the devices from the back, so it was not ideal. This year, we will have 2 new lasers mounted on the walls, and they will shine from the front. And the alignment can also be done fully from the outside thanks to a camera that can show where the laser is pointing. Then we will also shorten the vacuum pipe. So on this picture, you see the pipe is quite extended inside the IRAD, and the facility is already quite packed. So to recover some more space, we will cut this pipe and gain about 1.7 meters here and all these devices that we currently have. So the degrader system and the test station will be moved upstream. So the amount of air will be kept constant. We will just have some more space to, for example, reach the patch panel. Now, how do we perform the beam calibration and monitoring? So there is a set of beam instruments that are existing on the T8 beam line that we put into contribution. So first there is a scintillator that is very close to the extraction point from the proton synchrotron. So here it's indicated on the sketch with the arrow, so it's quite upstream, but still works reliably. We use the scintillator mainly to check the time profile of the beam on a spill-by-spill basis. So we check if within the spill the distribution of intensity is more or less uniform. It is measuring in arbitrary units, and no calibration is needed because we just check a profile. Then we also have an instrument for the spatial profile, which is the multi-wire proportional chamber that you saw inside the facility. It provides the profiles of the beam along X and Y, also doesn't need any calibration. For the beam intensity, we use secondary emission chambers that are located just before the entrance to the RAD facility, so behind the wall. There are two of them, and they provide intensity in row counts. So these ones, they need calibration in order to provide an absolute flux. And we complement these more standard beam instruments with a silicon diode, which is a commercial detector, very small one that we put in place, and we perform some more precise measurements. So the silicon diode can provide event-by-event energy deposition measurement. So since it is event by event, it can count very precisely. So this is what we use for the flux calibration. And then we also can verify the energy and the LET of the beam. So a word on the flux calibration. As I just mentioned, the two secondary emission chambers need to be calibrated such that then we can have the online measurement of the flux. We calibrated with the silicon diode, which is 2 by 2 millimeters square, and it's placed at a DUT location. So we are counting particles exactly as it is at the irradiation position. And the calibration method consists in making a correlation between the counts from the secondary emission chamber with the flux measured by the diode. Then we make a linear fit and we can extract the calibration factors that you see here. And we do this for all the different flux settings, which is represented here in the different colors. Of course, we also have to do the flux calibration with and without degraders, because if you put in place the degraders, the flux count is attenuated, and this has to be corrected. Once the secondary emission chambers are calibrated, we use them as flux monitors, so our users can get the flux information online. There are two of them, so they are called XSEC and X-ion, and basically the difference is that one of them can measure up to very high fluxes and the other is rather suitable for low fluxes. And here you see the demonstration when we were ramping down the flux across the full range. You see that the X-ion could measure here up to above 10 to the 5 ions per centimeter square per second, while the X-ion was saturated. Then for a large part of the range, they follow each other. And then on the very low fluxes, the XSEC cannot measure anymore, but the X-ion can. So with the combination of these two instruments, we can cover a very large range of fluxes that we can now adjust within the 10 to the 2 to 10 to the 5 ions per centimeter square per second. Then the energy and LET calibration. So as it was already quite explained by Andreas, the dosimetry of very high energy heavy ions is quite challenging. We performed this with the silicon diode, here is a summary of the method, which was also published in these references if you want to read the details. So basically the diode is measuring the event-by-event energy deposition spectra. You have an example of them shown here for the last year beams. Then we correlated them with spectra from FLUCA simulations, verified the linearity, And when the linearity is correct, we can use Fluka to extract the corresponding LETs of the beam. The LETs that we can cover currently with this facility range from 12 to the famous 37 MeV centimeter square per milligram. And finally, here's the overview of the beam parameters that we offer with HARTS at CERN. So we have lead ions that offer the LET from 12 to 37, as I just mentioned. The corresponding range in silicon goes from 1.5 to 50 millimeters, so they are very penetrating. The flux is from 10 to the 2 to 10 to the 5 ions per centimeter square per spill. In terms of timing, the beam is pulsed. The spills last for 1 second and arrive about every 10 seconds with a good homogeneity across the spill. And the beam spot is squared, as you can see here, shaped by the masks with 3 different sizes, which is also shown here from the measurement from the multi-wire proportional chamber. And the uniformity at the flat top is about 10 to 20%. Now a word about the user pilot run. So last year, for the first time, HARTS at CERN welcomed 10 external user teams. So we had 3 HARTS partners and 7 industrial users. In total, there were 33 people coming on site from 6 countries, and we successfully delivered 168 beam hours. As you see here, we had a lot of fun during this test campaign with external users. And here is also a little overview of the beam usage. So basically, you see that all the offered LETs were used, with some bit more preferred than other, but overall, all of the menu was used. Also, the full flux range was used, and in terms of beam size as well, mostly everyone preferred the smaller beam size, but also the larger beam sizes were used. So how does it look in terms of user lifecycle and support if you want to come to test at CERN? So before arrival, you first need to apply. We collect the applications, and then if you are accepted for a test, you need to start preparing your test. So the first thing to check when you want to prepare your test is the user guide. I will put a reference here. For the moment, it's a written document where there is absolutely all the technical information and practical tips that you might need. But this will ultimately also become a website. Then we organize technical meetings with users on a user-by-user basis, where we prepare with them their test and how to interface their devices with the facility. And we also send regular newsletter emails to the selected users when we inform them about what they need to know before coming to CERN. Then the users have to register to become to be able to come on site and follow the mandatory online training, as well as take care of the equipment shipment to here. Once you arrive on site, you need to go through a couple of formalities and also follow an on-site training that is mandatory. And on the test day, when your beam time starts, first you will do the setup preparation. Then just before coming into the irradiation room, the equipment has to undergo the electrical safety clearance to make sure that it is electrically safe before you can even irradiate it. And then you have the beam time. Finally, after the test, we need to make all the equipment that was irradiated checked by the radio protection, make it declassify. After what, we can return the equipment and we can provide the dosimetry logs for the analysis. A little word of how does it look during a radiation test based on our experience from last year. So the setup preparation happens in a dedicated preparation room, which is upstairs. It's quite large, so all regular users can prepare there. And there are also dummy patch panels that you can use to verify your devices with the correct cable length. For users that have confidentiality constraints, we have another room that is a bit more isolated, where they can be alone for the preparation. And then inside the IRAD control room, of which you see the pictures here during a user test from last year. So there is the user who is running the test. So this is, let's say, the bunch of people sitting here in an L disposition, they are two Hertz shifters. So here you see me and Andreas that are operating the beam and all the corresponding beam devices, such as the degraders, the XY station, etc. So the users can directly talk to us because they are sitting next to us. And then here behind us, basically, there is quite some space where the next user that will come in starts preparing. Then the equipment is handled in the corridor or in the buffer zone if it is irradiated. And finally, very quickly, we also care very much about the user feedback because we want to become a great facility. So last year we had an external consultant that is acted as an unbiased person to collect user feedback. He did this through the electronic surveys and also dedicated anonymous user interviews, and he provided us with quite some information. So just a word on the outcome of the evaluation. Overall, the evaluation from these first external users was very positive. You see here a little example. So overall, people were satisfied to come to here, which make us believe that we are on a good track to become a competitive facility. But we had also a lot of useful feedback for future improvements. And with this, I pass the word again to Andreas to show you some single event effects test results that we obtained with these beams.
Yes, thanks. So indeed, it's just to give you a very quick idea of, let's say, how we use the buffer time in between the actual user runs for our own internal testing purposes, let's say. So here in the next few slides, I'm showing the results that were obtained by our colleagues, mainly Andrea, Mario, Ivan, and Daniel, who were testing devices. Yeah, like I said, within the buffer times, and mainly at let's say ensuring that the results that we're getting on, let's say, a number of quite standard devices, or we call them golden chips, that these results are the same as obtained at other lower energy or medium energy facilities around Europe. So these are devices that basically traveled quite a lot, and then cross-checked with the heavy ion beams that we had during HARTS at CERN. So here you see the single event upset results that were obtained during the test campaign of 2023. Then going to the next slide, we have the single event latch up results also obtained from 2023, checked against the facilities UCL and RADEF. Not going into too much detail here. If you want to properly check this work, I encourage you to read the data workshop from NSRAC 2024 paper, and I believe there will be the reference in the reference slide of this presentation, which will be made available. Just continuing here. These are results that were obtained during the test campaign last year. So the DAC device tested for SELs at HARTS at CERN and NSRL, so the other very high energy heavy ion test facility. The analysis here is still ongoing, but is also submitted as an abstract to NSRC. But it's just to show that that indeed we are getting quite nice agreements with these devices when comparing different facilities, and it's a kind of cross-check that is being carried out continuously to ensure that what we are providing to the user, let's say, kind of makes sense. This was also done for single event burnout. Here again for HARTS 2023 data, and again not going into the full detail here, but very welcome to check in the data workshop paper. As a kind of a sidestep, we'd like to present you kind of experimental way of testing that has been explored over the past test campaigns. It was proposed by Ruben a few years ago, and is entailing a novel approach that simultaneously ensures a high LET as a high penetration within device with a continuous LET profile, as opposed to the usual standard LET testing. And so we mentioned it already a few times that this can be highly advantageous for a very complex component for which there is a very large uncertainty on the LET value at the sensitive location, either because the device is not very well known, or it could not be properly characterized before the test, or simulations show other values, let's say. So here this can be an approach that that could jump in. And the extra benefit of this is that when we are using this approach, which is simply using a single energy, single ion beam impinging on a target that has a thickness that is larger than the primary range of the particle, is producing a large secondary spectrum that is composed of all atomic numbers below the primary particle, let's say. And when we are getting this, where we are both simulating it and obtaining experimental results of this particle spectrum, we see that we have actually a quite nice agreement with the GCR spectrum that you find in space. So this was then verified through simulations and experiments. So when you compare these, the table shows that the ratios are actually quite satisfactory between experimental and simulated single event effects. And in addition to that, we see that the single event effect rate attenuation is relatively small in matter for fully fragmented beam, and that could open the door to ground level testing with fully fragmented beams. So basically here it is just to highlight this test approach, but we also have to mention that, of course, this is still very much R&D activity, and development and validation efforts certainly are still needed before we can offer this as a testing approach, if ever. So, but that's just a glimpse on let's say more scientific things that we are studying. In addition to that, we just quickly highlight the future prospects for HARTS at CERN. Natalia very nicely mentioned the current situation that we have, but we're continuously on the lookout of expanding our operation, let's say. And we are in the inception phase, let's say, of doing a study that estimates the feasibility of constructing a dedicated testing facility at CERN, which would then no longer be attached to beamline to the PS, but rather to the LEAR, so the other accelerator that Natalia showed. There are a few requirements that we put forward. The ability to be able to offer a much more expanded LET range, because now we are, let's say, capped off at a minimum LET of around 10 to 12, is that we'd have a more versatile ion source, which we can extract different ion species at different energies and covering a much larger LET range. This would require some hardware upgrades in the LEAR in terms of power converters. And the dedicated beamline and experimental area could benefit the operation quite a lot, since we are indeed still, let's say, kindly using the infrastructure that was built by other groups at CERN, and that we are allowed to use for our tests now. The benefit, in addition to the larger LET range that we can offer, is a much higher availability of the beam, because the PS is a very busily solicited machine during beam time, running protons most of the time. Operating on the LEAR would actually, we could run completely in parallel of the proton physics program at the LHC. But again, this is still in the study phase, and we very much need the space sector partners' expertise and external funding to get this to fruition. So here then, I think I pass back to Natalia for the closing remarks.
Yes, sorry, this is not closing remarks. This is the most important message of the
Yes, exactly.
So how can you apply for the beam time? Because as I said, we will have another user run this year in the second half of November. So there are two access modalities. If you want to do some more scientific access, then we encourage you to apply through RADNEXT. In this case, the beam would be free of charge, but it must be somehow research oriented, and there is an obligation to disseminate results. So the next RADNEXT call will be in May, as it was said in the beginning by Ygor. So it opens the 1st of May and throughout the whole month. So I encourage you to apply if you want to come to test with us. But we also offer a second access modality, which is more for purely commercial users that want to have a paid and proprietary access with no obligation to disclose the results. So for this one, keep an eye on the HEARTS website, where we will open a call most probably in June. So everything will appear on the website when it is ready. And by the meanwhile, if you have any questions, you can contact us on this email address here. And I leave you with this. Thank you very much. And here is our contact details if you have any questions after the seminar.